Yeah, very good morning to one and all. So here, let us start with the today's session here. So the last class we discussed about the different types of the geometric transformation. That is, one is translation, and another one is rotation, and another one is the scaling here. That is what the thing that we discussed in the last classes here. So the today is we'll move on to the next topic is introducing homogeneous coordinates. Introducing homogeneous coordinates. What is this homogeneous coordinate means? Suppose if you want to apply the geometric transformation, that geometric transformation must be always applied in what exactly in and sequences on a given object. That means it can be applied in sequences on a given object. Suppose for example, if you want to apply the any transformation here, first here if you want to perform the scaling here, how the sequence is to be is first translate, then scale, then again translate into your translate to the original position here. This is what we call this as the sequence of the transformation here. So usually the each of the basic transformation can be expressed in the general matrix form is p dash is equal to m1 dot p plus m2 here. So that means this is what exactly the general matrix. This can be used to apply the basic transformation here, where actually the P is the old position, P dash is the new position, and M1 and M2 is what exactly, these are all the identity metrics and also as well as the transformation metrics that can be used in order to apply what exactly the any transformation here. So here in this case, what exactly this homogeneous coordinate means? Whenever if you want to express, if you want to draw any images here, we used to write it in the form of what exactly in the xy plane here, that is x and also as well as the y plane here. So usually the matrix representation. So that means the each coordinate, the matrix representation can be expanded by using what exactly the two. Usually we used to do 2 cross 2 here. For example, if you want to perform the scaling factor will be like this. This is what, sorry, sx0 and 0 sy. This is what each thing has to be represented in terms of in 2 cross 2. So here the same matrix object representation can be represented. So the each matrix representation can be expanded by 2 cross 2 to what exactly the 3 cross 3 here. 3 cross 3 means x, y and z plane here. But instead of taking in z plane here, what we are specifying that this the Cartesian position, that is this Cartesian coordinate position with respect to the xyz can be expressed in terms of what exactly the homogeneous coordinate, that is what x, y and also as well as the z here. Because that usually in generally whatever the applications, whatever the transformation we are going to apply here, that will be based on what exactly x and y here. So instead of mainly considering the z plane here, what we are performing, so that 2 cross 2 matrix has to be and represented or the expanded by using 3 cross 3, where 3 cross 3 means the here the third row or the column will be represented by using what exactly the homogeneous coordinate here. So that means, so this can be represented like this, x comma y comma z. It is called actually the homogeneous coordinate here. So this usually this homogeneous parameter what we have actually the h, it is a non-zero value. It is an what exactly non-zero value. But the convenient choice for using this homogeneous coordinate, it's always what exactly 1 year. That means x comma y comma 1 year. So this is what exactly that means. What it says that each two-dimensional position, each two-dimensional position is represented by using what exactly homogeneous coordinate, that is x, y and also as well as the 1 year. Now let us see how this homogeneous representation can be represented, can be expressed with respect to the geometric transformation, that is translation, rotation and also as well as the scaling here. So for that You can see, that is what I told. You can see introducing the homogeneous coordinate. So this is what that diagram, it shows what exactly introduction to the homogeneous coordinate. So here x, y and z. Instead of the z, what exactly we have taken actually the h plane here, where the h is actually the non-zero value. That means the 2 cross 2 matrix representation has been expanded by using 3 cross 3, where instead of specifying the z plane here will be taken as in the homogeneous coordinate, and the always the convenient value for this h will be an plane here. Okay, and the basic transformation is represented by using like this: b dash is equal to m1 dot p plus m2 here. So the now is, we'll see, that is what I told. So the homogeneous representation for translation, rotation and scaling matrix. As we know that the translation is equal to what exactly? P dash is equal to t into p, right? So where P dash is the new position, T is the translation and P is the old position. When you apply what exactly translation with respect to the old position, we'll be getting what exactly? We'll be getting actually the new point. So the new position that we are expressed in terms of in the P dash here. How this can be represented by what exactly with respect to the homogeneous representation is? So as we know that x P dash is x, we usually we represent it in terms of 2 cross 2. There we usually we represented P dash will be what exactly? P dash will be P dash in the form of what exactly? P dash, we usually in the last classes we have seen that P dash has been represented by using what exactly? X dash and Y dash. So this is for 2 cross 2. When you are represented with respect to the 3 cross 3 with the homogeneous coordinate, then P dash will be represented as X dash, Y dash and 1 here. So like this, that is what the thing it is showing here. So the translation that you have to note down here. Translation is P dash is equal to T of Tx comma Ty dot P, where P dash is X dash Y dash 1. We have introduced, this is has to be represented with respect to the homogeneous here. So, and the T of Tx comma Ty is 1 0 Tx 0 1 Ty. It is represented in terms of 3 cross 3. Wherever we have the H value, there H values, homogeneous coordinate value has been represented by 1. Then x, y and 1. This is for translation. Next, rotation. Rotation, as we know that what is the equation for rotation? P dash is equal to r of theta dot p here. So that P dash is x dash y dash 1 and r of theta, that is theta values cos theta minus sin theta is 0, sin theta cos theta 0, 0, 0, 1. This is what the homogeneous coordinate. Then P will be x, y and 1. Next, scaling, same thing. P dash is equal to s dot p here. So it is how you are going to represent. This is x dash y dash 1, sx 0 0 0 sy 0 0 0 1. So this is what exactly the standard matrix representation for translation, rotation and also as well as the scaling here. So the new translation, rotation and scaling metrics can be used to perform the transformation. So these are all what exactly? These are all the equations that we need to remember, or the equations or the values we need to remember in order to perform what exactly? The geometric transformation. So the next is, we'll have the next topic, which is called actually the inverse transformation. What exactly the inverse transformation? So here the inverse transformation can be applied for all these three types of a geometric transformation. That is, one is translation, next one is rotation and another one is the scaling here. The first is, we'll be concentrating on translation. So here the inverse of translation can be applied by negating the translation distance here, by means negating the translation here. That means, for example, assume that, so when I apply what exactly, for example, suppose assume that I have applied what exactly, I have applied the transformations. I want to apply the scaling here or the rotation here. So in order to apply the rotation here, the C finally 2 0 minus 4, then 0 2 minus 3 and 0 0 1. This is what the value that you got. Yeah, right. So then P dash is equal to M into P. M is what exactly? P dash is equal to M is 2, 0, minus 4, 0, 2, minus 3, then 0, 0, 1 into P. What is P here? This matrix values. That is 1, X value 1, 3, 2, then 1, 1, 2, because we need to represent this in a 3 cross 3 matrix. That is, the third column will be homogeneous. Let us take 1, 1, 1 here. So this is X coordinate value. This is Y coordinate value. This is an homogeneous coordinate value. Then when you perform the multiplication, P dash, you'll be getting P dash is equal to minus 2, 2, 0, and minus 1, plus 1, then 1, 1, 1 here. Then after performing this, somewhere you'll be getting the object like this. That is P dash is minus 2 means, let us take this is 0, 1, 2, 3. This is minus 1, minus 2, and this is minus 1. This is minus 1, minus 2, and somewhere here plus 1 and plus 2 like this. So minus 2, minus 2, minus 1 means somewhere here minus 2, minus 1. X values minus 2, minus 1 and H value, then 2. Another one is 2 is here. 2, minus 1 and 1, and here 2, minus 1 and homogeneous coordinate, and another one is 1, 1, 1. So this is what the object you are going to get here after performing. This is how you can perform the fixed or pivot point scaling here. Got it, students? Got it? Is this clear? Is this clear for all of you? Is this clear for all of you? I'm asking you, is this clear for all of you?
Yes, ma'am.
Yeah, this is how you can perform the things here. Whatever we have done, that is fixed point or scaling or the rotation, scaling and rotation, that these value matrix values you need to remember. If you learn these matrix values, then it helps for you to execute the another program in your lab session also. That is rotate and triangle about a fixed or the pivot point here.